The Model-Based Embedded and Robotic Systems Group at CSAIL, MIT, collaborated with the Monterey Bay Aquarium Research Institute to develop a depth control algorithm for the Dorado-class autonomous underwater vehicle that conducts scientific underwater missions such as mapping the seafloor and detecting algae blooms. The model predictive control-based depth control algorithm has been successfully deployed. The algorithm improves the quality of scientific measurements by allowing the underwater vehicle to approach closer to the seafloor. This graph shows that our algorithm is more successful at maintaining the proper altitude above the seafloor. However, there is uncertainty in the position of the underwater vehicle due to unpredictable water movements and control errors. In order to avoid losing the expensive vehicle, a minimum altitude above the seafloor is prescribed for each mission. The mission aborts if the vehicle gets too close to the seafloor. So there's a dilemma. Good scientific measurements require close proximity to the seafloor, but getting too close results in mission aborts. Therefore, we need an intelligent controller that explicitly considers uncertainty by balancing risk and utility. Take race car driving, for example. The race car driver wants to get to the finish line quickly and safely without crashing into a wall. However, uncertainties such as road condition may cause the actual path to be different from the planned path. To minimize the distance to the finish line and guarantee that the probability of crashing is less than some acceptable level of risk, say 0.01%, the driver could set a safety margin that guarantees this risk bound and plan a path outside of that safety margin. However, the safety margin that guarantees a risk bound is not unique. If both margins incur the same amount of risk, for example, 0.01%, then B would be a better path because it is more direct. But why? This uneven safety margin takes higher risk at the corner, while it takes less risk at the straightaway. It is better than the other path because taking a risk at the corner results in a shorter path than taking the same risk at the straightaway. This observation leads to the notion of risk allocation. In order to maximize the performance under a risky environment, you need to optimize the allocation of risk. Taking a risk at the corner results in a greater time savings than taking the same risk at the straightaway. In order to optimize the allocation of risk, we developed a novel algorithm called iterative risk allocation. The algorithm is initialized with an arbitrary risk allocation and computes the best path given the current risk allocation. Notice that the constraint is active at the corner, but inactive at other locations. So we take the risk away from the constraints that are inactive by increasing their safety margin and reallocate it to the active constraint. The best feasible path given the updated risk allocation becomes shorter, but still there are inactive constraints. So we repeat the same process once again. We move the allocation of risk from inactive constraints to active constraints. Each iteration improves the risk allocation until it is optimized. We applied iterative risk allocation to autonomous underwater vehicle depth navigation. The improved results are shown here. Additional results can be seen in our forthcoming paper. All in all, our new algorithms allow scientific researchers to limit the probability of mission abort while maximizing the quality of scientific measurements. Our algorithm has a diverse range of applications from the control of aerial vehicles to energy-efficient control of smart residential buildings.